Assume the function below fits the form of L over 1 plus a e to the negative kx. It's a logistic function. Does it show logistic growth or decay? Well, since as the x values increase, our logistic function's values are decreasing, this is an example of logistic decay. Let's find L, which is that upper highest level of the logistic function. So according to the graph, L is 16. Okay, can we find the constant A from the graph by plugging in this value here? We see that f of 0 is 8. So let's do 8 equals 16 over 1 plus a. If you multiply to the other side, you get this. And divide. So 1 plus a equals 2, therefore a is 1 for this graph. Now can we find k using 1 point from the graph? I'm going to go ahead and pick this point, 1 comma 4. Looks like it'll be an easy one to plug in. So let's let our output of the function be 4. We'll plug in the 16 that we had found earlier. And for a, we'll use 1. And we'll get e to the negative k times 1. Okay, I'm going to need to simplify that. 4 times 1 plus 1 over e to the k equals 16. And then we'll see that 1 plus 1 over e to the k is 4. So 1 over e to the k is 3. E to the k is 1/3. Therefore, if we take the ln of both sides, k will be ln of 1/3. Okay, let's rewrite the equation now using everything that we had found. There we go. The function must be 16 over 1 plus e to the negative ln 1/3 times x. Let's check it just by plugging in a large value of x. And let's see if we get 0. I'll plug in 100. And yeah, it gives me an extremely small number. It's close to 0. Now I'll plug in an x of 1. We hope to get 4 as the output. Great, that worked. And let's plug in an x of 0. That gives us an output of 8. Perfect. Now let's try a really far negative number, like negative 100. That gives me approximately 16. Okay, perfect.